Record progress.
Yeah, ready to go. Hello everyone. My name is McPeake, and today I'll be presenting to you using remote sensing to analyze algal concentration and trends at Utah Lake. So let's get a quick outline of the project. We'll talk about the introduction to the problem. We'll discuss some of the methodology I used to actually analyze it. We'll discuss the results. We'll discuss some of the results and some of the issues or successes that I had, and then we'll conclude it out and take everything home. So to start with the introduction, we'll talk a bit about cyanobacteria algal blooms or CHABs first. CHABs are basically algal blooms that are containing what's called cyanobacteria, which are basically photosynthetic bacteria that have the potential to release what is called a cyanotoxin. The cyanotoxins are a bit ranging to a couple things, but two of the major ones that are particularly seen in CHAB waters are microcystis from the bacteria microcystin and nodularium from the bacteria nodularia. Cyanotoxins have a pretty wide range of health effects when they're ingested by organisms that include from very simple things like headaches and abdominal pain to more extreme things such as hemorrhaging, liver failure, or death on the more extreme end. So it's a very important thing that a lot of different regulatory agencies monitor for so that people don't just start dying at random lakes. Now, to take things more closer to home, we have here is Utah Lake, which is a freshwater lake in Utah Valley near Provo, Utah. It's pretty big. It's the third largest lake in Utah and one of the largest natural freshwater lakes in the western U.S. You see by itself, it's a pretty big lake, about 24 by 13 miles. But one of the important things to note is that during the summer months from approximately June to October, it has a pretty bad sea hab infestation during those times, particularly with the bacteria microcystin. So the Utah Division of Water Quality and a lot of other agencies in Utah actually monitor for algal blooms in this area. And part of my thesis research is actually analyzing algal blooms in this area, particularly what's in the water and what could potentially in the air, but that's a different story. But that led me to the goal of this project where I wanted to use remote sensing to analyze algal bloom concentration in trends of Utah Lake because I wanted to use that remote sensing to pair to my research roughly where the field tours were basically what are the concentrations of Utah Lake look spatially on remote sensing versus what I'm actually analyzing in the field. And that ultimately led me with the goal that I want to create a time lapse from June to November using chlorophyll A concentrations, the greenness concentrations from various vegetation chlorophyll. That was the main goal. So discuss how I actually did is that we actually to discuss how I actually did, we actually need to define the indices that actually measure either chlorophyll or vegetation in the area. And there's four major ones that I found that do somewhat this well. So the first one is a normalized difference vegetation index. So basically the measure of greenness in the area, and that uses both the near infrared band and the red band to do that. We have the normalized difference chlorophyll index, which is basically a unique indice as it explicitly measures chlorophyll or chlorophyll reflectance in hypereutrophic waters, which is the cause of algal blooms in the first place. It uses both the red edge band and the red band to do that. We have what is called the very aptly named band 8A band 4 index, which is just a measure of difference between the red edge 4 band and the red band, which uses, as previously mentioned, the red edge 4 band and the red band. And then we have what's called the aptly named band 3, band 2 index, which uses the green band and the blue band to basically just measure general chlorophyll in the area. So as you can see here is that two of the bands, particularly normalized NDCI and band AA, band B4, uses both the red edge and red 4 bands, meaning that Landsat cannot be used for those data sets. So in order just to make things easier and have one data set used for every single band, it's just easier for the situation to Sentinel-2 data. Now, for the actual coding process, is that this main work was done primarily in Python or Jupyter Notebook through the Google Engine API. There's a couple main steps here to do this, but the first step is that we need to define where Utah Lake is through a polygon. And now it's done just through point coordinates. It is possible to upload a direct shape file into Google or Python to get a better outline, but GIS is very painful to use for that. So I just decided to make a million points. Outside of that, we had to define the indices used for the function because while the NDVI in particular is used or commonly seen in mixed data sets, the NDCI and the BA, BA4, and the B3, B2 are not. So in order to do that, you have to define a function with those names, apply the function, rename it, and then apply it to the list of possible bands that the data set can use. After that, it's really just creating a collection of images, there's a collection of images, and then creating the time lapse and time series that follow it. And on the bright side as well is that there is, due to the Utah Lakes, I guess, habitat, there is actually a visual check we can use to actually analyze if the indices are working well or not. Is that right here is an area called Provo Bay. And the neat thing about this is it's actually a marsh attached to Utah Lake. So the idea is that it's always covered with vegetation throughout the year, regardless if algal blooms or not. So if the index is working well, we should be getting some hit of vegetation in this area at all times. We can use that to measure if the index is actually working well or not. So moving on to the actual results, we're going to start out. Okay, it's starting to lag now. We're going to start out with the NDVI index, and you can see a couple of things here. On your right, you have a still image of what the possible output looks like, and then you have a screen capture of what the actual timeline looks like. One of the issues I found through this is that while Python is supposed to have methods for G exporting GIFs, six different methods did not work at all, so I just had to screen record it. And you also notice if you look very close, it's kind of hard to see, but you see the very mountain or weird forms and those are clouds because for some odd reason you can filter out clouds in a Landsat 8 collection, but you cannot filter out clouds in a Sentinel 2 collection. It's just how the current state of the code works. But as you can see, the only hits we're getting for this is on the clouds. And if you compare it to the actual time series or reflectance up here, you can see that it never gets above the reflectance of 0, meaning it only measures negative values, meaning we're getting no reflectance at all, meaning that NDVI for this index was working particularly poorly. Comparing it to an NDCI index, on the other hand, actually gets a pretty good result. On an instrument left, you see it's pretty well colored. You get lots of hits, particularly around the coastlines. And here, as you can see through a time lapse, decided to not be super slow. You see you're getting a pretty decent hit at first from Provo Bay, and then during some of the more coastal areas, you're getting pretty good hits. Compared to the actual reflectance itself, it's kind of hard to see because, of course, that's there. But it ranges from a value of approximately 0 reflectance, 0.2 reflectance. While it's not the most, you're at least getting some level of hits for chlorophyll in that area. Comparing it to the B8, BA4 index, as you can see, still on your right, or still on your left, base on your right. Only hit you're getting is clouds. Provo Bay has no hits in it. And then the range of your reflectance goes from 0 to approximately negative point or negative 0.8. So again, this is much like NDVI, this index works very poorly. And then comparing it to the final index, which is the B3, B2 index, once again, still moving image. You're actually getting it's a lot more unique in the sense because it's primarily a black background, then you have areas of gray or green everywhere. Provo Bay is pretty highly colored. A lot of the coastal lines or some of the more funnel points are colored as well. Compared it to the actual time series itself, you can see approximately the same as, or it's very similar to the chlorophyll index where it's ranging from 0 to 0.2 reflectance. So much similar to that one, we're getting some hits. It's not the best, but we're working a lot better than negative 0.8. And then you actually just comparing all indices together, much as previously stated. You have a pretty decent line where B3, B2, and NDCI are getting some hits working pretty well, and then your NDVI and your B84 are getting really, really bad hits consistently. One thing is that the B3, B2 is a bit more, varies a bit more in its hits, and it's a bit more higher at times, but for the most part, or B3, B2 pretty much has a lot of spiky wings, while the NDCI falls a bit more trend, where it's relatively constant peaks, relatively constant peak, relatively constant peaks. That most likely correlates roughly to the algal bloom season every year, but it's not exactly sure. So just to discuss little points, as previously mentioned, NDCI and B3BU perform pretty well. And then there's a lot of issues that comes with this, primarily just through the current state of the code, where you can't really filter clouds from Landsat to or Sentinel data. There is a potential way around that, is that using Landsat 8 data, but by doing that, you cannot use pretty much most of the indices. But luckily, one of the indices that work very well, which is B3, B2 index, can be used in Landsat 8, so that might be an issue going, or could be a solution going forward. Another thing going forward is that the potential to use single image instead of collections, because if you just use Landsat 2 data to take a single image from a date range and just apply index to it, it works fine. You don't have to worry about cloud filtering because that works there. And you can also use, or at least I found you can use a bit more vibrant colors because trying to use these in the collection did not work as well. So in the end, it might just be better to use a single image from roughly when the tour field campaign happened. Pair that with the data instead of trying to make a time lapse in the entire series. So just to conclude things out, is that remote sensing can be used to analyze algal bloom concentration trends at Utah Lake. The NDCI B3, B2 indexes were the best performing ones. And due to the current state of module packages, it potentially might be better to use these single images compared to a single day than trying to collect the entire range for a single season. And that there's also a possibility of using a Landsat 8 dataset for B3, B2 in particular, instead of trying to use Sentinel 2 for that if you want. And that we have references. And are there any questions?